Hello everyone, so welcome back. So we have been discussing about assembly level language, and we looked at different aspects of assembly language, starting from machine models, how it actually dictates how the assembly instruction will look like. We looked into addressing modes, then we looked into different other apart from the arithmetic instructions, we looked into shift instruction and how shift instruction can be used very efficiently for doing arithmetic operations like multiplication, divisions. We also looked into branch instruction in the last lecture, and today we will be starting with a very important concept or important aspect of programming, which is called functions. So we will understand functions, what it is, and then we will also understand how it is implemented in assembly. And to do that, we need to also understand the concept of stack little bit more. We have been discussing about it about stack when we discussed about different machine models, but here we will see it more closely. All right, so let's dive in. So today we will be discussing about functions and how functions are implemented. So what are functions? So functions are basically block of instructions. So since we are talking about assembly level language, so basically in this case the function will be a block of assembly instructions. And why we need to write functions? So that we can if we need to do this operation repeatedly, so that we can just invoke that function, and that whatever that function does, that work gets done. So we don't have to write it again and again. So I am sure all of you are familiar with the basic construct of function in your high level language. So same concept or same fundamental thing apply here also. A function can be as simple as, let's say, whether to add two numbers. So if you repeatedly need to add two numbers, then you can write a function, and every time you need to add two numbers, you can just call that function. Similarly, you can write a function for, let's say, finding out whether any number given as an argument to that function, whether it's a prime number or not. So how in basically in your architecture or in your processor, how this function gets implemented? So function, as we could intuitively understand, will have an basically starting address. So for example, let's say this is my memory, and in the memory I have defined a function, and let's say call this function foo, because traditionally this is what the name of the function that has been used. So we will also use the same. So let's say these are all my blocks of memory, and function foo is defined here. So what is function foo? Function foo is nothing but set of instructions, right? So it will be telling that, okay, do this, do that, and so on. So it will have a starting address. So let's say this starting address of this function foo is a. Now whenever I need to call this function foo, so what we need to do? We have to set our program counter. So always remember that we are talking about assembly, so we have to think about how it will impact our program, our assembly level program. So it will basically somehow whenever I need to invoke this function, I have to update my program counter with this address, which is the starting point of this function a. Now, so one thing is like I need to call this function to perform some operation, but I have to also remember where I was, so that when I am done with evaluating this function, I should have a return address so that I can come back where I was. So basically we also need to store the location of the program counter that we need to come back after the function is evaluated and we have a return value. So this return address is called basically this address where we have to come back is called return address. So very simply, if we think about the execution of a program, so let's say I have been executing a program starting from here, and at this point I realized that I have to basically I got a function call, so I have to go to a different location, and that location is, let's say, A. I'll evaluate it, and then once I am done, I have to come back to this location, and then again basically from there I have to resume my work. So this address where I will be coming back is called return address. All right. So basically we can call any function and executes its instructions, and then the once we are done with it, we have to come back to the return address which has been we have to return to the address which has been saved as return address. So this we can look at it in a little more formal way. So let's say I have this program which calls a function. So this program which calls a function is called caller, right? It is calling a function, and let's say or let's say this was the program, and in this program, in instruction address P, I have an instruction which is nothing but a function call. So this is the address where this function call is stored. Now the return address for this instruction or this function will be the immediate next address, which is P plus 4, because we have this 32-bit instruction. So we are basically each instruction is separated by 4 bytes. So that is my next instruction which need to be executed. So that should be my return address. All right. Now the function which I am calling is called callee. So this is my callee function, and let's say the callee is this function is stored in this memory location, which starts with the location A, and then at the end of it there is a return instruction. So whenever I have this function call, so what I have to do, so basically at this address P, there is a instruction which calls a function. So immediately the next step will be you update your PC with the new address from for basically where the function is, and also you will basically save the return address which is PC plus 4. All right. So basically in the return address you will be storing PC plus 4, and here you will be updating PC with A. So this is what you do whenever there is a call function. Whenever there is a call function, you update, actually you first store the return address which is PC plus 4, and then basically update your PC with the address of the function, and then you basically so next instruction is executed from this location, and whenever you are done you look at what is the return address and you come back to this address to resume your work. So, you go from here and come back here, all right. So, I hope this makes sense. We can look at one simple assembly instruction to further understand this. So, let us say I have a code and the main, so just like in C we have a main function. So, let us say we define a main function here. So, in the main function we do things like let us say move R0 with the value 3, move R1 with the value 5. Now, my objective is to let us say add these two values. So, for adding these two values, let us say I have a function called .foo, all right. So, I have to define this function somewhere. So, let us say I define it here. So, this is the level where I define this function. So, what I do here, I simply write add, and I stored the value of this add in R2, and what do I add? I add two registers R0 and R1 and store the value in R2, and once my addition is done I return. So, basically what do I return from this function? So, I return the answer of this addition in this register R2, all right. Now, one thing you have to carefully observe here is that the values which the function needs are passed through these registers. So, for example, the function foo will need to add two numbers and store it in a in another register. Now, how these numbers are passed to this function? These are passed through these registers only. So, main updates these registers, and whenever foo uses them, basically it uses the value which main has updated, all right. So, if you look at the flow, you will see that okay, the main function main program was getting executed, then you call this function. So, as soon as you reach this call function, you will go to this level to start executing this function, and once your execution is done, you will come back to the next instruction which is after this call. So, let us say there is another instruction which we again do some addition, where we add these two numbers. So, let us say an immediate value 10 is added with R2 and the result is stored in R3. So, the level indicates the starting of the function here. So, if you see that okay, R0 is 3, R1 is 5. So, when they are added, R2 is updated with 8. So, when you come back from this function foo, so R2 is having the value 8. Now, you add 10 with 8. So, in R3 you will get 18. All right. So, this is a very simple, just to give you some sense like how a function looks like in assembly. This is how it looks, all right. Now, do you see any problem in this kind of approach? Definitely one problem we can immediately see is that the arguments which this function needs are passed through these registers. Now, these registers are very limited in number. So, for example, in our simple RISC, or if you look at ARM processor, we have only 16 general purpose registers. Now, you might have a you might want to write programs where there will be much more number of arguments that need to be passed. So, in that scenario we will not be able to pass more than 16 arguments, because you have only 16 registers. So, there is a problem of basically this resources or space. You do not have unlimited, or you do not have too many registers to pass your arguments. So, there is a problem of space. So, let me just write down that space problem. There is another problem which is related to, let us say I am calling something recursively. So, I call this function foo to do this addition. Now, I have another addition here. Okay, so, let us say in this function itself I can call recursively this foo, right. So we can look at one example. Standard recursion can be very easily understood by let us say the functions like factorial. So, if you want to calculate factorial, so you can basically recursively call this function factorial and find out the factorial answer for the minimum value, and then you I am sure all of you have seen examples like this. So, when you call recursively this function, now there is a possibility of overwriting, because you have only so you see these registers are getting updated here, and these values are being used in this function. Now, similarly, let us say this function is updating R2. Now, in your main, if R2 is getting updated differently, then there is a problem. You might overwrite R2 in an unexpected way. So, there is a problem of overwriting. So, how do you differentiate that? Okay, this is this value you are not supposed to or this register is exclusively used by, let us say, some function. So, I am not supposed to overwrite it and all these things. So, how do you ensure that? So, there is a problem of overwrite. So, to solve these problems, so to solve this space problem, we can, instead of only restricting ourselves to the 16 general purpose register, we can use memory also. Right. So, we will see how we can use memory. So, basically we pass arguments through some dedicated memory. That is where the concept of stack will be useful for us. Now, to overcome this overwrite problem, there is a we can do register spilling. So, what is spilling? So, register spilling is a simple concept and very intuitive also. So, the register spilling concept says that, like here the caller calls the function this function. Now, whenever caller calls a function, either the caller can do this. So, caller can save the set of registers where it does not want the values to be disturbed. So, basically in this example, if we come back, so this is our main program, or this is the caller code. So, let us say I do not want a specific register to be disturbed, just let us say R2. So, what I can do, before I call this function foo, I will store all these registers which I do not want to be disturbed. So, basically let us say I will just store R2 in some memory location. I am just let us say 100, and the offset is, let us say R4. So, I am just giving some memory location. So, in this case what I am doing, before I call the function foo, if I do not want to lose the value, or if I do not want to take any risk that R2 should not be disturbed, so I store this value of R2, and okay, so R2 may be a bad example here, because R2 is here used for getting the result back. So, let us say I am just writing down R3. So, R3, in this example R3 is not getting updated by the function, but I do not want to take risk. So, I will store R3 in this location, and then once I come back from the function, I will basically load it again, so that the value which I do not want to be get disturbed, that is stored safely before I go for serving the function, and once I come back I retrieve it. Alright. So, this is called spilling. So, as I said, like the caller saves the register. So, caller saves the set of registers, and then calls the function, and once the function returns, then it restores the set of registers after function returns. All right. So, this scheme where caller does this, so the program which is calling the function, it is making sure that the registers it does not want to be disturbed. So, it itself saves those registers and then calls the function. So, this scheme is called caller saved scheme. So, caller saved scheme means basically the caller is taking care of this responsibility of storing the registers before the function is called. There can be another alternative, which is, as you can possibly intuitively guess, is called callee saved scheme. So, what is callee saved scheme? As the name suggests. So, here the caller does not do anything. Whenever the function call is there, it just goes to that function. Now, here callee is responsible for saving the registers. So, basically whenever you reach to that function, callee function, it first saves the registers which is not being used for, let us say, argument passing or result passing, and then while returning, it restores all those values. So, this is just these two schemes which through which you can implement register spilling. All right. So, just pictorially, if we want to represent the spilling, so basically the caller scheme looks like this. So, you have your caller. So, first it saves registers, and then it calls the callee. So, callee does its task and then restore registers. All right. So, this is your caller saved scheme. So, basically caller saved scheme. The other option is, this is the callee saved scheme. So, here caller will not do anything. So, you reach to the callee, so callee saves registers, so callee saves registers, then it restores, alright, and then basically returns and all these things. So, this is called callee saved. So, this looks like a very reasonable solution, and you should be able to handle argument passing efficiently with this kind of spilling mechanism. So, and if you use memory for basically storing the register values as you will be doing, then you have actually solved both the space problem as well as overwrite problem, right, because you eliminate the chance of overwrite because you have already stored the copy, and then while you coming back you restore the original. And space problem you have overcome because now you have you have this memory where you can because of this memory you can basically pass lot more data. Now, to implement this, you need a very strict agreement between the different callers and callees regarding the set of memory locations that they will be using. Because let us say the caller, so this is your memory. So, caller was basically accessing this set of memory. Now, when your callee again tries to use memory, now if callee also tries to use the same memory, then there will be a huge problem, right. So, you need to have a strict agreement between all the functions in your which will be concurrently running, so that there is no ambiguity about who is supposed to use which memory. Also, there is a very important aspect about it, is that once the function is done its task, basically function the function returns, then this memory should be reclaimed as soon as this function is done, because if you can't reclaim, then like you will be eventually writing basically in your system there will be lot of functions which will be concurrently will be evaluated. So, now if you do not reclaim the memory which you allocate for a particular function in a timely manner, then your performance will get significantly degraded and you will soon run out of memory. So, basically what all things we need to do? We need to have a strict agreement between about how the different functions will be using the memory. So, the memory location each function will be using. So, strict agreement between the caller, callee regarding the memory usage. okay, memory location that needs to be all right. Secondly, the as soon as the function is done, function is finished execution, the all the space which was allocated to it need to be relocated. So, all the space need to be reclaimed as soon as the function execution is done. All right. So, I hope this makes sense intuitively. So, these are the requirements. So, how we will be achieving these requirements, we will come to it in a bit. But I think it looked fine in terms of conceptually how spilling will work, but how the arguments will be passed, it may not be yet clear, because let us say if you want to pass more than or you need to deal with more than 16 arguments, etc. So, there you will be using memory. So, as we said, like we can use memory for passing arguments, etc. Now, this memory which will be used for passing arguments, we will call it as activation block. So, what is activation block? So, activation block is nothing but a structured memory. Basically, we have certain fields in that memory. So, activation block will have, let us say, if this is my memory, so certain part of this memory will be defined as arguments. So, the arguments that need to be passed for a particular function. Then we need to also have some dedicated space for return address, depending on whether there is a recursive possibility, etc. Then there is this register spill area. So, basically where you will be saving your registers. And finally, you have your local variables. So, a function will do all its activities in this activation block. All right. So, I will just write it down that it is a so what is activation block? Activation block is a memory map of a function functions and its arguments, register spill area, local variables, etc. So, all the things which is related to this function will be done in this memory block. Memory block of a function and it contains this arguments, register spill area, local variables, etc. All right. So, basically whenever you call a function, this activation block will be created, where you will have a designated place for the arguments, the return address, register spill area, and local variables. All right. So, how it will fit into this whole scheme of thing? So, let us assume a specific model. Let us assume the caller saved model. So, in a caller saved model, basically caller will do the spilling. Okay. So, what will happen before calling the function? Let us say this is my caller code. So, it has different instruction. Now, here there is a call function, a call instruction. Now, basically before it goes to that that function to execute that, what it will do? It will create, it will basically first save the basically the spilling will be done by this caller. So, it will create this activation block. Alright, so it will create this activation block. And then it will move to the callee. So, it will allocate a so first of all it will spill the registers and then it will allocate the activation block of the callee. It will write the argument to the activation block. So, all these arguments that need to be passed in the passed into this function, they will be written in this activation block argument field only. Sometimes basically if the registers are not enough, so that is what you will be doing, and then you call the function. Alright. So, basically the sequence is you spill first, basically you save your current registers, then you create the activation block and then write the arguments in the activation block, and then you start basically call the callee, so that the callee can start executing. Okay. What happens in the inside the called function? So, it will read the arguments and if it needs to do some arithmetic operation, etc. So, those arguments can be transferred to some registers. Then it will also save the return address. So, basically if there is a recursion, etc., and it will use the local space for doing or executing the function. Now, once the function ends, what you will do? You will restore the basically you will figure out what is the return address, and all the return variables or the arguments that need to be returned to the main caller function. So, all these things are written to the activation block. Basically all these things are either written to the register or through the arguments it is passed, and then you destroy the activation block of the callee. So, once you return from there, you destroy the activation block of the callee. All right. So, basically once the function ends, you find out the return write down the return instruction and return to the caller. So, what the caller does, it retrieves the return values from the registers or from its activation block and restores the spill registers, and then it continues. Okay. So, all this information and information about how you can execute a function is stored in this activation block. Now, this block need to be dynamically created and destroyed, because you will be dealing with lot of such functions. Now, what is the easiest and the best way to implement that? Now, if you look at the specific look at the pattern in which these functions are called and then their values are returned, etc., there is a pattern. So, if you just look at that, so let us say I have a main function So, this main function, let us say, calls a function called test, alright. So, this is a function. Now, this function again calls a function called, let us say, test2. So, now how the return will happen? So, first once the test2 execution is done, then it will basically return to this function, and all the things which was reserved for this test2 I can now basically reclaim, because once test2 is evaluated I do not need it anymore. Similarly, I come back here, I do everything, and once I am done with this test function and I hit the return, then I come back to the main function again, and here I can again reclaim everything which was allocated for test2. Similarly, if I want to, if I look at another example, let us say I have another function foo. So, this foo calls another function called, let us say, foo bar. It can again call another function called, let us say, foo bar, right. So, what will happen? So, you will go in this direction, basically you will be calling function after function, but once this function or the function which is called latest, once that is done, then you will come back to the previous one, and then you will come back to the previous one, and so on. So, there is this pattern, and this is a very interesting pattern to look at. Now, remember that every time I call a function, I have to have this activation block associated with that function. And if we look closely, the pattern here is that, let us say, whenever I go to this function, I will create an activation block for this. Then when I go to this function, then I will create another activation for this, and when I go to this function, I will create another activation block for this. So, this is the activation block for this function which will be created latest, right. And then once I am done with this function, I will be reclaiming this activation block, or I will be basically deallocate that memory. So, you see that I will create this activation block latest, and I will also deallocate it fast before any other activation blocks getting deallocated. So, once I deallocate that, then I come back here and then I look at basically execute it, and once that is done, then I deallocate the activation block for this one, and so on. So, here the thing to observe is that we are following some kind of a last in first out. So, the activation block for this foo bar is created or created last, and it gets reallocated or reclaimed also first. So, there you have this last in first out phenomena, and whenever you have this kind of a last in first out phenomena, we know that stack performs very well, right. Because if I just like a book of stacks, the book which I have put on the top of the stack, I can remove that one first only. I will not be able to remove a book which is much lower in the stack, right. So, now let us say so traditionally these stacks are basically downward growing stacks. So, what do I mean by that? So, let us say I have a memory which has the capability of storing, let us say, 1000 bytes. So, what I will do, I will denote my stack pointer, or I will be my stack pointer will be pointing towards the highest memory, the 1000, alright. So, this is the top of the stack. Now, if I just look at the allocation block for this this chain of functions. So what I will do, so from main when I call foo, so I will be I will be saying that okay, allocate this much memory for foo, let us say 100 bytes, just an example. Okay. Now this is allocated. Now next let us say foo calls another function foo bar. So next I have to allocate another activation block. So how can I basically allocate this activation block? So now when I allocate this location as activation block for foo, how do I do that? I can very easily do that by just changing my stack pointer. So if it is 100 bytes, so I can just say that okay, add 100 with my stack pointer and let us save that as my new stack pointer. So basically now this location is allocated for foo and nobody else, basically I'll not be I can make sure that no other program uses this memory location, because now I have updated my stack pointer. So now next time any other activation function need to be allocated, so now my new stack pointer is this location. So since this is a downward growing stack, so this will be stack pointer minus 100. So basically now my stack pointer will be pointing towards this location 900. So now if I want to allocate another activation block, what I can do, I can just look at, or I can just from my current stack pointer I can allocate, let us say again 100 bytes, and I can say that okay, this is the activation block for foo bar. So I can ensure that there is no overlap. Similarly, if I want to allocate activation block for foo bar, so what I have to do, I have to basically whenever I do that, I will be updating my stack pointer by 100, and that will be my new stack pointer, which is 800. And for foo bar I can do the same thing, and basically this is foo bar bar, right. So now this will update my stack pointer to 700. So any new block I need to activate allocate. So this is my stack pointer with respect to which I will be allocating new blocks, etc. Now how do we reclaim? So again reclaiming is very easy with the stack function. So whenever I need to reclaim this block, what I will do, I will just add, I will change my stack pointer to this location. So basically I will update my stack pointer as sp plus 100, and that will point towards this location. Now if I need to reallocate something, so my stack pointer will be pointing this location and I can reallocate this space. So this is very easy and intuitive to implement. So what we have said is that let us say this is my stack pointer, which is the highest address that can be basically depending on, let us say as in our example I have 1000 bytes as my stack, and this stack pointer now points to 1000 bytes, that location which is the highest location. And then basically whenever I want to allocate, depending on how much I want to allocate, I will be updating my stack pointer. So let us say if I want to allocate this much, then I will be updating my stack pointer saying that okay, this is the new value of my stack pointer. So assuming that these are 100 units, 100 bytes or 100 words, whatever you want to say. Similarly, if I want to allocate something more, then I will be updating it again like this. And for reclaiming, so basically this is allocation, and for reclaiming what we will do, I will just keep on adding or deallocating. So, basically you will be updating your stack pointer by this many locations. So, basically you can allocate allocate and deallocate very easily using stack pointer. So, how we will implement it? So, if you think about it conceptually or hardware wise, stack is very simple. So, basically this stack concept or the management of stack is mostly done at the software level, because at hardware level you really do not need anything apart from possibly a register which will be storing the value of stack pointer. So, you can define a part of your memory as your stack, and this stack is downward growing. So, the first activation block starts at the highest address and the subsequent activation blocks are allocated in the lower addresses. So, in our simple RISC, actually the stack pointer register which I have already mentioned is register 14 is used as stack pointer, and also register 15 used as return address. All right. So, for activating or allocating activation block, what you will do, you will be just updating your stack pointer with basically stack pointer minus the size of your allocation block. And for deallocating, as we have seen, that you will be basically updating your stack pointer with basically adding that constant which is proportional to the size of your stack. All right. So, now what this stack has solved? It has solved the space problem. So, you can now pass on as many parameters as required in the activation block, because you have an activation block. It has also solved the overwrite problem, because it has now activation blocks. Activation blocks are non-overlapping, so there is no overlap possible. And also you can easily manage this activation block, because managing this activation block may not be very easy, but you can manage this activation block by using the concept of stack, and this stack is primarily managed at the software level. All right. So, just to summarize what we have discussed so far. So, through stack we have so we have solved the space problem. Because you have activation blocks for passing parameters. Passing as many parameters as you want. Overwrite problem. Okay. So, this is solved by the again the activation block. And management of activation blocks, that was an issue that has been handled by stack. Okay. And these stacks are managed at the software level. So, before concluding, very briefly how basically call and return instruction look like. So, basically let us say you have a instruction like call.foo. So, what it will do? It will first save the return address as PC plus 4. So, so remember R15 is your return address, and it will also update the PC with the address of foo. And what will return do? So, return will just update the PC with the return address register. All right. So, basically the call instruction puts this PC plus 4 in the array and jumps to this location where the function starts, and the return instruction is pretty much like a jump instruction. It's basically updates the PC to this new location, and it comes back to your original location. All right. So, there is a very simple assembly code in the book for basically factorial calculation, which explains the activation block very well. So, I would encourage you guys to go through it. If time permits, we will also try to see it in the class. All right. Thank you.